Everyone, thank you for coming. My name is Daniel Hockman. I'm a software engineer at Lyft. I've been operating Redis in production for a little over 4 years now. This is my third time attending the conference and second time speaking, and my sessions were largely inspired by conversations that I had had with other attendees. So the theme of this conference, or the theme this year of the conference is everywhere. All of the various deployments of Redis, I think, are very interesting, and we all have a lot to learn from each other, which I think is why we're all here. And as engineers, we spend a lot of time, listening and asking questions and reading, and some of our time writing code as well. Even when I wrote this abstract for this talk, we were at 1,000 instances, and the scale of Lyft and the growth of Lyft, now we're at 2,000 instances. So that's only in a few months. So the agenda today is that first we're going to talk about how we built Redis from the ground up. So basically, how are we provisioning clusters? How are we running them? What are the different tools we use to actually route requests between nodes in the cluster? And the second thing we're going to talk about is high availability. And I'm sure if you work on distributed systems or you work at a large company, you have heard the term high availability. You have heard something like, we want to be available for 99.99% of the time. But to put that in real terms, if you think about it, if you do the math, and someone can check me, but that would mean that you could take a Lyft twice a day, every day, for 13 and a half years straight, and you would only have one problem where you couldn't take a ride. I mean, that sounds pretty hard to achieve, right? So we're constantly trying to, achieve 99.9% or 99.99%. But we have to understand, basically, how we're able to do that. So we're going to talk about how we handle the different failures, and we're going to talk about the different load testing techniques that we use to ensure that our system can remain available to give people a good experience no matter what's happening in the data center. So this is just a brief callback to my last year's talk. The first half of it, I talked about scaling a geospatial index. So we iterated over the data model and talked about how Lyft does things at scale with geo, because the Redis geo commands are great for prototyping, but don't really work in a clustered scenario. And the second half of the talk was focused on operating Redis on the Lyft platform. And this was really about the tools that we use to integrate into the organization. Something like a spreadsheet where we can track the capacity of all of the clusters. This talk is going to differ a little bit, and then we're going to go at a lower level and look at how we're actually running the cluster, and then again focus on high availability. So the talk is available on YouTube if you do want to check it out after this year's talk. So let's just look at the numbers. I presented these at last year's talk, and this is less than a year later. Maybe, I think it's been 8 or 9 months. So last year we had 50 clusters, 750 instances, and we were doing 15 million QPS at peak. Our Redis infrastructure was based entirely around Twin Proxy, and if you don't know what that is, don't worry, I will go into it shortly. But fast forward to 2018, right, and we've seen a tremendous amount of growth in our Redis infrastructure. But one of the major points I want to make is that we were able to migrate the entire infrastructure from Twin Proxy to Envoy. And again, I'll explain what these components do and how they work in a little bit. But the interesting thing about this is that we don't have very many resources dedicated to Redis internally at Lyft. In fact, I'm the only person that's actually dedicated to working on Redis at Lyft, and it's not even my full-time job. So a quarter of my time is spent maintaining Redis, and we have a lot of help from the service teams. At Lyft, we don't have SREs. The mantra is kind of you build it, you run it. So everyone is kind of responsible for maintaining their cluster. And the way that we're able to do this and be so flexible and scale so easily without throwing lots of resources at it is that we eschew consistency. So we don't run with replication. We don't run with AOF or RDB. We don't save the data. We tell everyone at Lyft that Redis is a best effort cache or a best effort store. So if you put data into it and you do a write, you may do a read and not get the expected result back. And we don't give any consistency guarantees. And if we lose an instance, then all of the data is just gone. And so one of the things that's different about Lyft as compared to some other services is that we are a very real-time service, right? We've got this live marketplace that's happening where drivers are matching with passengers and pricing is constantly fluctuating. So data, as soon as it's written, it's basically out of date anyways. So even if we were to, in some of our clusters, flush all of the data out of the cluster, within 5 seconds, it would be completely refreshed. So that means that we don't need to worry about something like keeping a backup of that data because restoring it would be pretty much pointless. So let's explore now from the ground up what we can do. And let me just make another point, though, about consistency, because I think this kind of ties our whole infrastructure together. it's going to be that we don't always need to return data from every node. Let's say we have a 3-node cluster in this example. And let's say you're standing outside and you're trying to catch a ride to the airport, and there are 9 cars around you. If we only know about 6 of them, we can still give you a ride. So if we want to have that 99.9% available experience where you can take a Lyft, every day for a year and not have a problem, it's not going to matter if we can't return data from one of the instances. As long as we have partial data, we can remain available and have, it may be a degraded experience from a user experience perspective. We may not pick the optimal match, but if we can return some data, that's going to be good enough, to keep things running. So let's, again, explore how we build a cluster at Lyft. So the way that we provision clusters at Lyft, we don't use Elasticache. We run them on our own VMs in EC2. And every Redis cluster is basically an EC2 autoscaling group. So each service is responsible for defining and deploying its own cluster. And what an autoscaling group is basically a way to just apply templates to a group of instances. And you can say, give me more of them, give me less of them, and that's no problem. So you would find an example like this alongside the application code itself. So the same way that we deploy the application, we deploy the infrastructure. So they can define a cluster, and we have some boilerplate, and you can say how many instances you want. If you want to add more instances, you can adjust it, redeploy, no problem. Everything is managed in there. So there's no central repository where people are coming to ask for clusters. Of the 64 clusters at Lyft, I've probably only personally worked with 30 of them. The rest have been stood up and are humming along, and a lot of them are pretty small use cases, 3 or 4 instances. We mostly work, or I mostly work with people on the larger clusters, figuring out how to scale them and how we can unlock, more throughput for them. So once we have kind of an instance, right, we need to provision it. And this is a slide I think that everyone can take something from. So if you've ever looked at the Redis configuration file, it's over 1,000 lines, and a lot of that is comments, but it's very difficult to read, to follow. Even in version control, it can be difficult to work with. So one of the nice things that Redis gives you is the ability to actually include the defaults, or include whatever you would want as a config, but in our case, we include the defaults, and then we can just set the overrides. So this makes it very clear to anyone who's working with Redis, who has ever worked with Redis, how the Lyft installation may differ from what would happen if you were to just say, install it from your package manager, right? So we can see here that durability is turned off. We're not doing any save. Some things we allow application owner to configure. So if you look at max memory policy, we have a default, but we allow people to override it if they want to. So that's what we do there. And another thing that we do, since we have so many clusters and we can't, the service teams are managing them, we're not managing them ourselves, is that we do try and disable some commands. So Redis has this nice feature called rename command. And what you can do is if you alias a key to an empty string, that command will actually no longer be available to run on the Redis instance. So this avoids kind of what I like to call the Stack Overflow syndrome, right? Where some engineer has run into a problem, they're trying to figure out what's happening, they go on Stack Overflow and they see, okay, I can look at everything in my database by running keys. But if you were to do that on most of the Lyft instances, Redis would block for multiple seconds. And we can't afford multiple seconds of downtime for debugging. Another thing you can do is actually rename a command something else. So let's say that we do want to provide access to the config capabilities, the real-time config capabilities of Redis, but we don't want people cutting and pasting random commands or just running it randomly. If we rename that command, it's going to look like it's not available to that person. And we can even give it a nice name like be careful so that they're very aware of what they're doing when they're using it. So yeah, we have Jinja templates, and this is all done using SaltStack when we boot the instance from that provisioning script that we saw in the instance template. So once we have an instance, we need a way to talk to it, right? If we're spinning up 60 instances, there's no way from the application that we can talk to 60 Redis instances efficiently. So before, again, this is deprecated internally at Lyft, we were using Twin Proxy. Another name for this is Nutcracker. All of the code says Nutcracker. I think they just renamed the repo when they were open sourcing it so that it sounded nicer. And if you've been to RedisConf or if you've done a lot of reading on Redis, you've seen many large companies running with Nutcracker. But unfortunately, it is unmaintained. So if you look at the commit graph on the bottom, there has been no activity, meaningful activity, since mid-2015. And it's been replaced with a closed source product. So internally, Twitter is now running with something called Nighthawk. And there was a presentation last year from an engineer from Twitter Rashmi, and you can find that talk on YouTube as well. It's very interesting, but this is not available to anyone but Twitter. There is no active health check, so if you give it an IP of an instance and its static config file, and that instance doesn't exist or doesn't pick up the phone, it will try and route commands to it anyways. It doesn't actually care, so you'll just get errors back in your application. There's no hot restart, so if we do want to make a change to the config file, we're going to have downtime. And we can't afford, again, 20, 30 seconds of downtime waiting for some daemon to restart if we want to remain 99.9% available. And the final thing is that it's very difficult to extend Nutcracker. So it's an old legacy code base. It's been through a lot of iteration. But the biggest problem is that it has very, very little test coverage. So it has no unit tests, and it has like 3 integration tests. One does a get. I think another one does mget. And that's it. So if you're making changes in there, it's going to be really difficult to know whether or not you're just breaking everything. So what did we do? We started to invest in using Envoy for Redis. So Envoy is an open source proxy, and it's primarily built for edge and mesh networking. So that means that you can think of it as a replacement for something like Nginx or HA proxy. I mean, it has a lot more capabilities, I think, than those do. But that's the traditional role that it will take on. It has lots of observability. So we run it everywhere at Lyft, and that lets us see if on any application, what is the error rate, what is the latency, without having to integrate that into the application itself. It has dynamic configuration. So you can use a static config file if you want, but you can also use a management server, which can either push config or have Envoy pull for that config dynamically. And this all happens at runtime and seamlessly. You won't have downtime while you restart Envoy waiting for it to pick up a new configuration. And then it has a pluggable architecture. So if you want to add something new, like Redis support, it's just another piece of the architecture. You don't have to do a lot of major refactoring. The constructs are all there for you to build new functionality easily. As I mentioned, it's out of process. So if you're in Java or Node.js or Golang or PHP or Python, it doesn't matter because you will talk to Envoy the same way that you talk to whatever you were hoping to talk to anyways. So if you're speaking HTTP to a backend service, you'll just talk HTTP to Envoy instead, and it's going to proxy that request for you. It has a thriving ecosystem. So we have here a lot of companies on board. It's pretty exciting, and it's starting to reach critical mass in kind of the microservice architecture world among a lot of companies. Not all of these companies obviously are using the Redis capability that we're going to discuss, but I do know of at least one other large company that is using it. So at Lyft, we use Redis and Dynamo and Mongo, and all of these are actually supported by Envoy. And of course, we'll focus on Redis primarily today. So now that we understand a little bit about what Envoy is, how does it actually build a cluster? And the first thing that we're going to talk about is discovery. How do we understand who the members of the cluster are? So we have a Discover API, which is backed by some database, and every 60 seconds on a cron job, we will just post up to Discovery and say, here I am, a heartbeat, basically. And the Discovery service will store that data. Then every 30 seconds, on a 30-second interval, the envoys will ask the Discovery service, who are the members of the cluster? And it's important to note that this is an eventually consistent membership system. So that 30-second interval that those envoys are on, it's not going to be the same 30-second interval, right? They may be offset by 5 seconds, by 20 seconds, whatever it is. So they're going to see changes in cluster membership at different times. And this is in stark contrast to most other database clustering systems, where they want to know exactly who the master is, and they're only going to send requests for that key to that master. And if you have downtime in your discovery system or your gossip protocol, whatever it is, if you have an issue there, you're just going to be faced with hard downtime because nobody knows where the data should actually live. So when I talked earlier about the lack of consistency, that frees us up to have a very simple discovery system in comparison to a lot of other clustering solutions. We have active health checking. Again, this is something that Nutcracker did not offer. So we can send a command periodically to check for a healthy response. So the most simple one that you can imagine would be we're just going to send a ping, and we'll get back a pong, and everything's good. We can have a connect timeout, or the request itself may time out, and we can mark that as unhealthy, but most of the time it's going to respond with a ping. If the instance gets terminated unexpectedly, it won't respond, and we'll eject it from the cluster membership. But there's another type of health check that we use at Lyft, which is actually we check for the existence of a key. And if the key doesn't exist, we assume that that is a passing health check. And this allows us to actually go and proactively mark instances that we know need maintenance or termination. So Amazon will send us a notice that says we're going to terminate this instance in 2 weeks. We don't want to wait for that. We'll just go and terminate it now because it's probably on degraded hardware anyway, which is why they're terminating it. So we can just go and set a key. All of the traffic is going to stop going to that instance, and then we can terminate it, no problem, no impact to the application, and no downtime. We also have passive health checking, and another name for this is outlier detection. There's two types of outlier detection. One is detecting consecutive failures. So here we can say if you see 30 consecutive failures from an instance, assume that there's a problem with it. There's another type, which is looking at the success rate. So you can compare the success rate of all Redis in the cluster, and if there's one that's not acting similar to the others, that is failing a lot more often, you can go ahead and eject it. And outlier detection is nice because, again, you're not actually putting additional load on the cluster to do health checking. Even with ping at some of our cluster sizes, we can do 10,000 requests per second just on health checking. So we can actually increase the interval of the active health check, the ping, so that we get less frequent pings, and we can have a tighter outlier detection window, which just wastes compute on the Envoy side and doesn't actually take any resources away from Redis itself. And there's another thing here that's important to note that is called panic routing. So you can imagine that if you had some service that was calling your service, which had Redis, and it started calling it more and more, and the service started to have trouble keeping up with the load, you might start to see one instance go unhealthy because it was getting too much load. Well, what's going to happen to that load? It's going to be distributed to the remaining nodes. Now all of those are going to start going down, and you can just have this cascading failure where basically you have no instances left, and all of the load is just directed to a single instance, which can't keep up with it. So there's a threshold that says if let's say 66% of the instances are having trouble, if they're not healthy, then we're just going to route to everyone anyways because the service is probably in trouble for other reasons than Redis. So this is an important way that, again, we maintain that availability, even in the case of an edge scenario. Okay, now I'm going to attempt to explain consistent hashing in 2 minutes. I don't think I'm going to be successful, but maybe it will be a foundation for some people. And there are just some points when we were running with this algorithm at Lyft that I think are important to make and will inform some of the future decisions that we're making. So as I said, Envoy is mainly an advanced load balancer. So it has different load balancing policies. One of those policies is round robin. One of those policies is least requests. We have another one called ring hash. And ring hash is an implementation of the Katama algorithm. The way that this works is that you will take your members of the cluster, and for each member of the cluster, you will take its IP, you will append maybe 0, 1, 2, 3, 4, whatever your in is, the number of times that you choose to hash it, and you will get an integer. And then you will place that on what is called the continuum. So the continuum is this ring here, which is basically, at some point of the ring, there are servers. And then when you get a request, what you do is you hash that key to an integer similarly, and you find the range that it falls in on the ring. So in the case that we have here, in the examples we have here, we've got the red server at 15 on the ring. Let's say this is a ring of 64. And we hash the key, and it's 10. So the blue server hashed to 1, the red server hashed to 15. That means that key space belongs to the number 10. And so that search is a binary search to find which node is the closest one to the key that you're looking for. But if you've ever run Nutcracker, there's something buried in the code, which is there's a constant in set there. And it's set to 160, I believe. The larger you set in, the more times you hash each server to the ring, the better distribution you're going to get among nodes. You can see in even this example, the highlighted red area has more space on the continuum than anything else. So you may see that in production as this instance is taking 5-10% more traffic. As you increase n, you're going to get better distribution. Unfortunately, the cost of this is that it will take longer to initialize the ring, and you're going to have a longer search time when you're looking for it, for hashing each individual operation. So now that we have all these components, we have discovery, we have consistent hashing, we can actually go ahead and do partitioning. So what we do is that we run Envoy on every single host alongside the application, and the application will talk over localhost, over loopback to Envoy. It will send its commands as if it was just a logical Redis instance, and we're going to hash them as we said. And then we'll send back the result as if it was a single instance of Redis. So to the application, it really doesn't look that much different than talking to a single Redis. Again, we do sometimes have failures here, so maybe one of the nodes that we send a request to is not available. We can still return a partial response so that the application can try and remain available. There are some unsupported commands, and this is just a problem with the kind of partitioning in general on top of a protocol like Redis. If you have multiple keys in a command, you can't actually perform that command reasonably. So let's say we were trying to do sunion, and those keys exist on different boxes. Well, obviously we can't ask Redis to do the union in memory of it because it doesn't know anything about key 2 on server A. That key lives on server B. So we could fake it by, let's say, asking for all of key 1 and all of key 2 and just computing the union ourselves. But the union right could be orders of magnitude larger than, or the original sets could be orders of magnitude larger than union. So in general, we shy away from trying to implement something like that. There's a solution which is called hash tagging, and this is where you can actually designate a portion of the key for hashing. So we can say, we put curlies around a portion of the key, and that's what we actually use to allocate it to the backend server. So we can have other metadata in that key, we can have other differences in the keys, but we can be sure that they're going to be on the same server. Okay, so now that we understand roughly how Envoy Redis works, how we do discovery, how we do consistent hashing, and how partitioning in general works, let's talk again more about maintaining high availability. So if we want to remain available, like I said, 99.9% of the time, we have to think of the exceptional cases. It's not enough to just think about an instance randomly failing, which we do, and we try and design the application for. You have to think about the data center flooded, the power went out. You have to be aware of these types of situations and actually account for them. So let's just talk about, again, the base case, which is recovering from failure. We lose an instance. We have to rebuild the ring and compute, once we get from discovery that instance is gone or the active health check tells us that the instance is gone, we'll rebuild the consistent hashing ring in order to determine where to map those keys. And then once a new instance is added, which I think in our infrastructure takes about 5 minutes, the autoscaling group will automatically replace any instance that is terminated for any reason. It will automatically get re-added to the ring by the whole discovery process. So our cluster will become at full capacity again within 5 minutes. And the nice thing about consistent hashing and why it's used most commonly is that we're only reallocating a portion of the key space. So anything that was previously allocated to the red server will now partially be reallocated to every other cluster in the ring. And that ensures that when you have one membership change, you don't change the entire topology of the cluster and lose all of the data. But we had a problem early on when we were doing consistent hashing and testing this, and that is the number of times that you have to rebuild the ring. So as I mentioned, when we lose an instance, when we gain a new instance, when the active health check fails an instance, or when outlier detection or passive health checking ejects the instance, we have to rebuild the ring. And initially, we were building the ring on the actual worker thread that was serving requests. This wasn't such a great idea, and what would actually happen is that it took 500 milliseconds to compute the ring for our largest cluster. We had a 400 millisecond timeout on the operations. So what would happen is that outlier detection would start saying, well, all of the operations are failing, so I'm going to eject this instance. And that would just cause another rebuild of the ring, and it would just cascade over and over and over. Eventually, it somehow sorted itself out. But we did require a lot of optimization here in order to fix this. One of the things we did was to move that computation onto a different thread than the one that serves requests. But in some of our working with Google, we discovered that there is another consistent hashing algorithm. And they published a paper in 2016 about a load balancer. A lot of it is about just how they manage packets. But there is a consistent hashing algorithm in the paper called, and Maglev is the name of their load balancer, so we just call it the Maglev hashing algorithm. It's 10 times faster to build a ring. It has 5 times faster selection versus the binary search of Katama. And there's less variance actually between hosts. So we get really good distribution with Maglev. The only downside is that there's a slightly higher key redistribution when we change members. So I think in practice, it's like 0.5% more keys get reallocated versus Katama for a 100 node cluster. And the way that it accomplishes this is using lookup tables instead of rehashing everything every single time there's any change in the membership. So most of the lookup table stays constant when there is, for example, a single instance that joins or leaves. Let's talk about fault injection. So a lot of the infrastructure here, I think, there's opposing forces, basically, right? Amazon is trying to build the most reliable platform possible. They have people spinning up instances with their personal workloads that they expect to run forever with no degradation, with no problems. Lyft is running thousands and thousands of instances, and they can die at any time. But it doesn't happen, all that often, and it may not be all that noticeable to people who are, running the application, or they may get paged in the middle of the night with a blip and say, okay, well, that only happens like once every 2 months. I'm not really sure what's going on. So instead, and this is inspired by Netflix, which they call Chaos Monkey. We're not using their version of it, we have our own version. But what it does is it goes and it proactively kills members of the cluster to test that our instances and our applications can handle this behavior. Otherwise, it may only happen once a month. We may not really understand it. So instead, we do it during business hours, we alert the service owner, and they can actually monitor the behavior of the application when an instance dies. And similarly, we may design an application that can handle instance failure, but over time, as we ship more changes to it and as we add more code and there become more dependencies in the code, it may no longer work correctly. So if we do this at a regular cadence, we're actually testing, that they're following that consistency guarantee, that they're not expecting, the data to be completely durable. Otherwise, people will say, yeah, sure, the data's not consistent, but they'll build an application that assumes it is anyways. And this is a pretty major problem, I think, in just doing a lot of broad infrastructure. The other thing we do at Lyft is fault injection. Currently, we only do this at the HTTP level. So what we can do is take a portion of requests and actually inject latency, make them take longer. One of the fallacies of distributed computing is that the network is reliable. The network is inherently unreliable. There are always problems. Many times they're not visible, but we need to understand whether or not the application can handle increased latency. So even if that only happens once a month when there's a problem between two of Amazon's data centers, we need to understand that the application is going to be able to handle it. And another thing we'll do is inject errors themselves. So you can imagine if we have an application, let's say its whole job is to display a pop-up telling you have a coupon at the beginning of a ride. It's a dead simple service. It may run for years without going down. But inevitably, its disk will fill up, something will go wrong with it. So if we can actually inject errors from every service, we can tell whether or not they're going to have a meaningful impact on our ability to serve rides to get people where they need to go. So we want to do this at the TCP layer. We can inject, again, latency. We can arbitrarily coast connections for some percent of requests. And then someone contacted me on GitHub. They have a project called Redfi, which stands for Redis Fault Injection. And they're actually doing this at a per command level. So they will say for all GET requests or 10% of GET requests, just return an empty response or return an error or add latency. So they have very similar goals, and I think we're going to work together on integrating some of the Redis-specific stuff into Envoy. Let's talk about stats briefly. I presented this a little bit last year, but we have a one-line macro, basically, a function call that people can add to their repository and a dashboard file that will give them 9 different graphs with Redis information on it. So again, we expect everyone to run their own cluster. So we need to make it really easy for them to gain visibility into what's happening. But stats don't always tell the story. So if you look at this graph, the top one, for example, you'll see that there was a sharp increase in operations on one of the instances at 1 p.m., despite the overall command per second not really changing that much. You'll see that one instance has significantly higher CPU than the others, more than double. So how can we actually rationalize what's happening? It's very difficult, right? The application is tens of thousands of lines of code. It's going to be really hard to just kind of reason about what's happening. So what do people most often do when they want to understand what's happening at the Redis level? They run monitor, okay? And we've all seen tools like this or written our own, but you can take the monitor output and you can basically say these are the top keys, these are the top commands to try and understand a little bit more about what's happening. But we found actually this bug, and what would happen is that there was an unbounded, they would basically append to a hash and never expire it out. So the hash would just grow and grow and grow, and although it wasn't that large, it was accessed very frequently, and it caused a lot of additional throughput to occur on that Redis server. So the way that this works, if you pass the estimate throughput flag into the code, and this is open source on GitHub, you can find it at the link to the top right there. What it will do is it will take the top 1,000 keys, and it will go back and ask Redis debug object for the key. Redis will return the serialized length in memory that it has for that object. So whatever encoding it's using, if it's zip list, that'll be affected by that. But it does give us a good estimate of how much throughput this thing requires. So we just multiply the number of times that we saw it accessed by the serialized length returned by debug object, and we have a good idea of what's happening here. So Redis CLI has this big keys feature, which I had actually never heard of, but it's sampled, and you may even not have a very large key, it's just accessed more frequently than the others. So big keys can help, but I've also written this little tool that will actually go back and ask Redis for the size of the object to try and determine a little bit more. I have a couple of other tools that I'm not going to share today, but one measures context switches between, basically all that Redis is doing is switching context between memory and network. So it will actually look at the number of commands that are happening on the Redis and the number of context switches and try to give you an idea of how efficiently you're treating Redis. Are you using the proper pipeline size? Are you can use pipelines, but you don't want them to be too big so that you can interleave commands. So looking at the context switches, from the kernel will actually tell you a little bit about what's happening. And we've started to use this internally to debug some of our larger clusters and our larger scaling issues, where again, we're not quite sure why Redis is not able to go beyond a certain number of operations. Let's talk about serialization. So if we have a large object, that can be really bad for our application. But in general, less is more throughput in this case. So if we use a smaller serialization format, we'll do less memory. We'll have less memory consumption. We'll be doing less memory I/O, and we've actually saturated memory bandwidth at Lyft on one of our clusters. So CPU is fine, everything's fine, but we're saturating the memory bus. Lower network I/O is another benefit, and you'll have lower serialization cost probably at both sides. So both at the client, who is receiving the message from Redis and trying to put it into whatever language data structure it needs, and at Redis too, when it's pulling the object out of memory and sending it over the wire. So you can see some examples here. MessagePack is like a drop-in replacement for JSON, and we were able to save 30% of our resources, more or less, by using MessagePack. If you go a step further and use protobuf, which requires a strict definition of the object, you can actually get it down 82% smaller. And it does this mainly, it uses binary formats, but it doesn't send the key across with every object. So it just knows that in position 0, the key is called name, and that's what it's going to send back. There was actually one trick that we did real quick before I move on. We have a Redis cluster that is basically entirely dedicated to storing 64-bit integers in sorted sets. Sorted sets are strings for the key members. So what we did was we just took the 64-bit integer, we compressed it to a binary format, and I think we saved like 70% of the load on the cluster just by making a 2 or 3 line change. So always think about the size of your data and how you can get it smaller, particularly as you start to reach some of the upper limits of Redis. And how do we know when we might need to make changes, to our systems? How do we know if we're going to be able to survive, the spike of rides that occurs after the Super Bowl, on New Year's, during Halloween? So the earliest way that we did this was actually just by injecting extra bytes onto each object. So you can reason that if we have an object that has the drivers on the road, and we want to know what it will be like for there to be twice the number of drivers on the road, we can just add twice the number of bytes to that object. And that's going to load Redis more heavily because again, the more bytes you have in your objects, the more cost it's going to be at every layer of Redis, basically. We tried doing oplog replay, which is basically taking monitor output and replaying it at a much higher speed. So if you're doing, 10 writes per second and you play the log twice as fast, you could be doing 20 writes per second instead. This is really difficult because it's hard to, there are impacts basically on the number of connections on the throughput of the cluster. So if you're trying to replay, let's say, from a single instance, and you're trying to do it over one connection, that's not going to be representative of doing the same kind of traffic across 100 instances and 100 different connections. So we didn't really go with that much further. But an effort has launched at Lyft, and we've dedicated significant resources to this called simulated rides. And what this is a practical load test in production. So not only do we test the business logic, but we're testing the infrastructure. And this test is run on a weekly cadence. So again, how do we know, yeah, we designed our application to handle some load, but applications are deployed many times per day, many times per week. They're constantly undergoing change. How do we know that we didn't introduce a regression that will cause significant additional load at peak? So what we actually do is create fake drivers and fake passengers and put them on the road. The system knows how to handle them appropriately so that other business systems are not impacted. Like we don't look at the numbers and say, wow, we did 200 million rides yesterday. We're actually able to tell and differentiate the rides, and that was probably the hardest part of the project. But the benefit now is that we can apply as much load as we want with any profile we want. So if we want to simulate a night like New Year's where there are very large spikes after midnight when people want to go home, versus an event like Halloween where people are just in general going out and it's more of a slow ramp, we can use different load profiles and test them against the system. And this hits every piece of the infrastructure. So we don't have to design a specific Redis load testing system or specific DynamoDB load testing system. We can just test the entire system with this load. And it's not an easy project, but it's definitely worth it in the end compared to trying to maintain some of these other things and have them be analogous to real load. Let's talk about Spectre. So the first week of January, that we saw a 25% performance loss on all of our clusters, or most of our clusters, and we were pretty concerned, right? We didn't know if we were going to make it through the weekend. We didn't know what the impact would be at peak, because this is a significant change in the way that the load is being handled by Redis. So what we did is we did a load test, and we found every cluster that was going over some threshold. And it turns out that the hypervisor architecture of C5 is different enough from C4 that it didn't really have an impact on these instances. And furthermore, they're already a newer generation of hardware. They perform a lot better. So again, because we don't run with durability, because we don't have to care about losing all of our data, we're able to do the migration pretty easily in 3 days with about 3 people. And I think we migrated over 500, maybe more instances, probably close to 1,000. And the nice benefit of this is that we actually saw a 20% performance gain from before. So you can see in the graph, we've got week over week. The current week, when Spectre hit, the patches hit, the load starts to diverge and is significantly higher than the week before. Once we roll out the C5 patch and migrate the instances, the load drops significantly. So we bought ourselves several months of headroom by doing this. So that's most of the talk. I did want to briefly touch on roadmap. So Envoy currently has feature parity with Nutcracker, except for the hashtagging feature that I mentioned, although a lot of people don't really delve into that. But in order for there to be more uptake with Envoy Redis, what I want to do is write documentation or a blog post that gives some minimal configuration for Envoy as a Redis proxy. So it turns out that there's probably only 30, 40 lines that you need to configure Envoy to be a Redis proxy. But Envoy does a lot of things, and the documentation is very verbose, and it's easy to follow for some cases and not for others. So I think publishing a minimal config on how do we migrate from Nutcracker, or how do we just get started with Redis partitioning using something like Envoy, assuming that we don't need the durability requirements, and maybe you'll use something like Redis cluster for that, then I think it'd be really helpful for the community to have an example of this. We do want to actually add replication, and not Redis replication. We actually want to replicate writes among multiple nodes in the ring. And if we get an error, we can just go to another one. We don't have to maintain read replicas. This is effectively a multi-master type scenario. And at Lyft, and at a lot of systems, honestly, the profile is 10% write traffic or 5% write traffic, and the rest of it read traffic. You think about a social media service, and even Lyft, most of the traffic is read traffic and not write traffic. So we can afford to replicate it by just doing multiple writes everywhere and still doing reads on those same instances. And finally, we want to add request and response dumping. This is what I call the op log. And we look at monitor output, but if you're running 100 nodes, it's not very representative of what's happening from the application side. The application could send 30 commands, and you may only see 2 or 3 of them if you're looking at a single node in the cluster. So instead, what we can do, since we're already buffering the whole protocol in Envoy, we can just dump out the operations that are happening. And it's very easy to see from a request context what exact operations were happening and understand how the application is working. Because again, even though someone wrote the code, that doesn't mean that they understand how it will necessarily behave in production. So giving insight into this, I think, is going to be particularly useful for our developers. So that's all that I have today. Thank you for attending again. You can find me on GitHub and Twitter at Daniel Hochman. Again, look out for my blog post. I think I do one per every 5 years or so. And but if you'd like, please also participate in Envoy open source. So this doesn't mean writing code into Envoy, but let's say you take a look at the docs and you want to use it for something related to Redis and we don't have the feature, open an issue. Someone may pick it up, it may get prioritized. It may sit on the backlog for a while, but it's going to be really informative for us to understand what capabilities we need to add to Envoy open source. And Envoy is completely open source. There is no open core and paid version. It's all free. And then finally, Lyft is hiring, so if you're interested, you can talk to me or one of my colleagues that's here, or visit us on the web. And that's it. I'll open the floor up for Q&A. I think we're doing microphone Q&A at these sessions. If not, you can come talk to me. Okay, there's a microphone. There.
Can you please comment on hashing at proxy level versus hashing at client level to distribute the keys across nodes?
So you're asking at hashing at the client versus the proxy level?
Yeah.
Yeah, so for us, right, if we were to hash at the client level, we would have to re-implement that in every language that was going to do that kind of hashing. So let's say we had, a Python application and a Go application. We don't want to have to write the same code twice. This is why the out-of-process architecture is so powerful, because we don't have to re-implement, we don't have to maintain. Another thing that's been a huge pain at Lyft is just dealing with libraries and library upgrades. So let's say we did write a library that did this hashing, and we discovered a bug, and we want to roll out a new version. Deploying that, getting every application to update the library and deploying, 200 applications is going to be almost impossible to do. It's going to take a lot of effort. With the out-of-process architecture, it's very isolated. We can deploy a change there with no impact to the application. There's no downtime for the application, and it gives us very, extreme control over what's happening there. So that's why we chose to go with, this out-of-process proxy hashing versus doing it at the application layer, which I know a lot of people also do.
Thank you.
And that's the consideration for not using the Redis cluster offered by AWS as well?
I would say that Redis cluster just has very different goals than we have. So again, we talk about durability. At Lyft, we want throughput, and we don't actually care about durability. And we want availability, don't care about durability. So Redis cluster, I believe, uses Paxos, and it's not very mature, I think. I mean, Redis cluster has made some pretty great strides, and the spec is pretty impressive with how detailed it is. But I haven't talked to too many people using it at scale. Last year when I attended the conference, I think there was a session from Flickr on Redis cluster, and that was the only one that I had heard of, and even that installation was pretty small, I think, compared to a lot of the clusters that we run. So hopefully this year, I'm going to hear more about how Redis cluster has evolved and how production ready it is, but the goals are just inherently different. Again, our membership and discovery system is dead simple. And in fact, if you look at this, we can actually just bring the entire discovery system down, and Envoy can cache the membership in its memory. So if discovery is unavailable for 5 minutes, we can actually continue running with no problem. So there are less points of failure, basically, when that happens, as long as we have the membership information already.
So what is that discovery?
Discovery is how you determine the instances that make up the cluster, right? So when we launch a new instance, it's at 10.0.0.1. How will the proxy know where that instance is? It looks in discovery and says, give me the IP addresses and the ports for all the Redis instances that are running, and then that's how it knows who belongs to the cluster. Similarly, if a member leaves, it will notice an update in discovery that says this instance is no longer available for the cluster.
So though it's really early days, do you see yourself moving to Istio on top of Envoy?
We are looking at Istio. We're working a lot with the Istio people actually on a lot of the API specifications. Initially when we first started, for those that don't know, Istio is like another layer over Kubernetes that is basically for doing a service mesh, which is this microservice architecture with a networking component. It's something that we're evaluating. But right now we have our own kind of internal system, and first we need to kind of get up to speed with the current state of the open source APIs. And we're also working on other reference implementations. So we'll see if one of them wins or what happens, but Istio is definitely something that's very interesting to us.
Thanks.
Hi. What is the, I don't remember you said, what is the size of your cluster?
So our largest cluster, I think, is 500.
I mean, the size of the data.
So that's one really interesting thing about Redis at Lyft as well, is that we don't really have that much data. If you look at the memory consumption of most clusters, I think it's like under 5%. Almost all of our workloads are CPU bound because we're just purely asking for throughput. When you look at the concurrent active users of an application like Lyft versus the concurrent active users of an application like, let's say, Twitter, right? You're going to have a lot of people tweeting and reading. At Lyft, there are a lot of people taking rides, but it's not the same order of magnitude. It's a lot different. So in practice, we just don't really consume that much memory, and our clusters are sized purely on the amount of CPU that we need. There are a couple that are memory bound, but hasn't really been a concern.
So we have time for one last question.
So as an Envoy client, do I interact with Envoy APIs or directly with the Redis APIs?
You interact directly with the Redis APIs, yeah, if I didn't make that point. If you're talking to an HTTP service that Envoy is proxying, you don't really know that it's there. The goal of Envoy is to make the network more or less transparent. So you're talking to what looks like any other HTTP service, any other TCP service, or Redis service, and you're speaking the same protocol. It's when things start to go wrong or you need something more advanced, that's where all the stats come in. We can actually see what's happening at the network layer. So for example, Lyft talks to Stripe. And if you just drop in the Stripe client, it may start throwing exceptions one day when something happens with their API. You have very little visibility because you don't have access to their load balancers. So what we do is we actually are just sitting in the middle basically and saying, hey, this is the latency that's happening, this is the error rate, and we can observe that even for our third parties. So not only do we use this for internal mesh networking, for Redis, for DynamoDB, for MongoDB, we use it as well for interacting with third parties. And the very powerful thing is that it gives us just visibility on everything that's happening at the network layer. So we can actually trace the requests and see where the latency was at different steps. Was it allocated to this application or not? Just because Envoy is sitting there and emitting trace data back to a vendor we use called Lightstep.
And how does it compare with Netflix Dynamite?
Netflix Dynamite, again, it's more concerned with durability. They've done a lot of great work on what I call coordination. So right when they're bringing new instances up, they're warming them up with the data. They're doing lots of replication. It just has different goals, I think, than Envoy. So I think it's a really cool product. We looked at it briefly when we were starting, but we had this component, right, that's battle tested at Lyft, that's being used by lots of other companies as well. And we saw an opportunity to do kind of a minimal amount of work with adding the Redis protocol and getting all of these benefits. So like all of the stats that we already have, for example, we could curl and we used to curl the Nutcracker stats API and emit that data back into our stats system, but we just have everything native and we can add whatever we want. It's much more flexible for us with the tools that we already have to use Envoy versus something like Dynamite. But they're different projects and you need to ascertain what your requirements are and then figure out which solution makes the most sense for you. Okay, thank you everyone.